Hello everyone, thank you for coming to this VCell math model tutorial. That our goal is to use the VCell math model to simulate dynamic systems. So this model will be going through the Rinzal-Lee model. This is a model that aims to explain pancreatic beta cell activities. So before I go into the model, I would like to give you some background information about the biology that behind this model. So pancreatic beta cells are the cells that are responsible for secreting insulin after glucose stimulation. Insulin is the hormone that helps human body to lower the blood sugar. A deficiency in insulin secretion leads to diabetes. For a very long time, people observed that when pancreatic beta cells are stimulated by glucose, the cytosolic calcium exhibit an oscillatory pattern. So here on the top graph is the change of cytosolic calcium over time in beta cells. You can see there is like very nice oscillation. It's like they go up and they go down. Meanwhile, the membrane potential of plasma membrane shows a pattern that is a combination of fast oscillation, basically all the spikes, on top of a slow oscillation, which is like the slower one, like the one that is more corresponding to calcium changes. And for a very long time, people have been trying to explain this oscillatory pattern. Rinzal-Lee model is one of the early models that try to describe the phenotype. This model has three different equations. The first one describes the change of membrane potential. The second one describes the change of the opening probability of voltage-sensitive potassium channel. The third one describes the change of cytosolic calcium. So the membrane potential is influenced by the calcium influx from the voltage-dependent calcium channel, which denoted as ICAV here. So the V suggested that the calcium influx changes when the membrane potential V changes. It is also influenced by the potassium efflux through either the voltage-dependent potassium channel, which is denoted by the IK here, and as well as the calcium-sensitive potassium channel, which is denoted by this term here. And it is, of course, also influenced by the iron leakage through the plasma. So here are some more detailed equations that describes how all these channels work. So the second equation is describing the change of opening probability of voltage-sensitive potassium channel. All these voltage-dependent ion channels are derived from the Hodgkin-Huxley 1952 publication. And this is also true for the one that describes the change of opening probability of voltage-sensitive potassium channel. Let's move on to calcium. So the cytosolic calcium is influenced by the influx of calcium from extracellular to cytosol, which is written here, as well as the calcium sequestering happened inside cells, which is described in this term. Note that there is an F here. The F is the parameter that describes the fast calcium buffering in cytosol. So for the alpha here, the alpha is used to convert calcium influx from current into concentration. We will talk a little bit more in a bit. So here are some rest of the equations. All are from the Hodgkin-Huxley model. I'm not going to dive into this at this time, but just in case if you want to do an implementation on your own, you can definitely try. And this is the parameters that this model uses. It is very important to keep the unit the same. Also note that for this term, the change of concentration is used in the unit of micromolar per microsecond. So I'm going to stick to this unit in my future calculation. Let's talk about alpha. Alpha converts calcium influx from current into the change of concentration. And the conversion here uses a Faraday constant. What we do need to make sure is that the unit match, because if you look at the Faraday constant, the unit is given as MPa, second, and molar. while our concentration would be focusing on micromolar per microsecond. Here are the exact calculation I did. The bottom line is this is the alpha. Let's dive into VCell. We just go to the new, go to math model. Since this model is non-spatial, so we just select for non-spatial. When we just created the math model, you can see there's a math description, and then there is a compartment subdomain. So for the compartment subdomain, which is here, it's going to be the one that where we're going to input the differential equations. But let's start with math model. So think back in our slides. We have the model, we have the differential equation, and then we have a constant. So let's start with constant. VCell is very nice. You can type const, and then you will have constant, and just select it and hit return. I will define my first constant then. So for the Faraday constant, this is how I would read the Faraday constant. And then I will put a space between the name of the constant and the number of the constant. Faraday constant is 96485. And then end with a semicolon. This is very important. And also, what is also important is that hit apply changes to make the changes final. If there is a bug, so for example, I forget to hit the semicolon in the end, and I hit apply changes, this will tell me there is something wrong. And here it says, oh, it's actually telling me it's like line 1, column 8. So just go back check. So this is about constant part. So just for the interest of time, I'm going to copy and paste the rest. Okay, hit apply changes. Okay. The second thing we need to define is the variables. So here in our ODEs, on the left, you can see these variables like the membrane potential, the opening probability, and then the cytosolic calcium. So the syntax for define variable is volume variable. So here you see it come up. So just select it and then type the name. Remember that at the volume variable here, it doesn't end with a semicolon. So after you type the name of your volume variable, that's it. Just hit enter. Then I will input the rest of the volume variable, which is here at the bottom. And the other one. Okay. So to make sure there's no problem, just hit apply changes. And it's always a good idea to keep saving your model. So save as, I will call it example. Let's save it. Okay, so now we have all the constant and we have all the volume variables. The next step would be input functions. The functions are how alpha or beta is calculated, or simply like how the Vm or the Vh, the shifted voltage change, is implemented. So when we input function, let's start with function, which is this one. Like for example, if we call it Vm, that would be the name of the function we are computing, and how we are going to compute it, that is going to be V plus 50. And also end with a semicolon, and then apply changes. Also, for the sake of the time, I will just paste the rest into it. Okay. So one of the cool features that VCell math model has is adding annotation. So the way adding annotation is very similar with C. So for example, you have double backslash, and then you just type something, for example, like potential shift. And then hit apply changes. And so then let's move on to the compartment subdomains. This is where the ODEs are being inputted. Type ODE equations. It actually pumps out. So it has an autofill. So here it is the autofill that asks for the variable name, asks for the rate, and asks for the initial value. So let's use member in potential as an example. The variable name is defined here as a V. So here we just input V. If we go back to our, and then the rate is how fast the membrane potential changes. And if we go back to our slide, this is where we need to input our rate. This would be a negative ICA as we inputted before, minus IK as we defined before, minus IKCA, minus IL, that's the leakage. And then with the whole thing divided by the CM. Like in the equation, we write it on the left, but now we need to put it on the right. So for the initial value, since it doesn't really matter that much here, we just input a random initial value here, and we define it in before. So yeah, basically VCell will give you a template, and you just need to fill everything. For the interest of time, I'm going to copy paste the rest of it into it. So now we have our model ready. So let's go to the simulation. So in mass simulation, by clicking the new simulation icon, you can have a new simulation. You can change the name here. For example, I want to call it my trial. And then you can go to this button, which is Edit Simulation. So I will start with editing solver. So there are many different solvers that are implemented in VCell. You can use any of them, but in this case, for personal preference, I will use just CVODE solver. So you can also ending the starting time and the ending time. Since the starting time is also always going to be 0, then I want to add it to ending time. So in this case, since my model is counting one time step as 1 millisecond, and I want something maybe like 1 minute, so that will input 60K here. You could also fine-tune the error tolerance, but in general, I don't touch this. And also, since I don't necessarily need to keep every samples I have in my simulation, I can keep every 10 samples and up to 5,000 samples. This is more for preference. So for example, in parameters, you could change any parameters. So for example, if I don't want to my initial membrane potential as a hyperpolarized state, I will give something like lower. So for example, like minus 60 millivolts. Now we can do simulation. This is the button for local simulation, and this is the one that's for running the simulation on the server. Since I don't necessarily need that, I can just run it locally. So here it goes. So here you can see the calcium oscillate, and here you can see the membrane potential oscillates. So in the original VCell Lee paper, I sent out the parameter that gives in his figure 1 is slightly different, which is something that I can show here. So just for convenience, I will duplicate my first trial and I will just add it. So in paper, so the graph, the KCA was in a slightly different parameter, is 0.053. And the simulation it is much longer. It's something like 80 seconds. So I'll just hit run. And in the original paper, it does show how the voltage change with the simulation result. You can compare the simulation result with what is in the paper. So they're pretty similar. Okay, so that includes the basics of using VCell math model. So I will take question from now. Milda was asking about whether I can do a parameter scan. Yes, I can. So I'll still go back to this one. So for example, if I want to do a parameter scan of the sequestering speed of calcium in cytosol, I can scan it by just clicking the scan box. So I could either scan in a range or I can just scan in the list. For example, I want to see what happens if there's no calcium sequestering, if there's only half of the calcium sequestering, and what is the current calcium sequestering, and what if I have double speed of calcium sequestering. So I will do it. However, if I use parameter scan, I have to run it on the server. So this might take some time. The simulation result just come back. Let's look at it. So this is to look at what would happen if there's no calcium sequestration, when the calcium sequestering is at 0. So so this is the original parameter. Like you see a voltage oscillating, and you also see calcium oscillating. However, if there's no calcium like sequestering inside the cytosol, the calcium just going to keep increase, and it doesn't oscillate. Because you can see here, the voltage pretty much stay at a stable range. So if I have half of the calcium sequestering, compared to with the original one, it's like the voltage change in the similar range, but the period of oscillation is different. So we can have a better comparison by using this time plot with multiple parameter values in it. So for example, I can select 3 different variable sets. Like on the keyboard, I'm holding control while I'm selecting the other parameter. So you can see set 1 and set 2 corresponding to value 1, which is 0.01, and value 2, 0.02 of the calcium sequestering speed. So when the calcium has a lower sequestering speed, the calcium and the voltage oscillation is slower. The slow voltage oscillation is slower, and there is a shorter time span for the fast spiking on top of the slow oscillation. So anything else you want me to show you?
How about can you put in logic functions for the ODEs?
Logic function. I'm actually not sure how to do that. I can try. So for example, if I only want the change of membrane happens between 0 and 60 seconds, I can potentially put like t smaller than 60k. Let's see how this happens. Oh, it actually allows me to do that. Okay, let's try this again. Let's use the second trial because it's longer already and it doesn't have to run on the server. Okay, so I think this is what happens. Like when the voltage is only changing before the 60 seconds, which is 60k milliseconds, you see a very nice slow oscillation with fast oscillation on top of it, but then it's stick. I think we can definitely use this in the future.